Okay, 13 minutes. All right, hello everyone. I'm Hong Yeo. I'm an associate professor here at Georgia Tech. Today I'm going to talk about soft nanomembrane sensors and electronics that I'm working on, and I'm going to also talk about how we can integrate them with different types of robots. In this talk, I will deliver a high-level overview of ongoing research in my group regarding sensors and electronics. So if you want to get details, then please ask me later, or you can even visit my website to look at published articles. All right, this is my research group at Georgia Tech. We have a very talented group of postdocs, multiple graduate students, and undergrad researchers. So as a team, we are studying fundamentals of materials, mechanics, manufacturing, machine learning, and system integration. And based on those knowledge, we are developing and manufacturing different types of soft material-based nanomembrane sensors and electronics. And here in this slide, I included a few ongoing projects right now in the group where we are developing wearable and implantable biosensors and bioelectronics. And recently, my group got a few grants with other guys here at Tech to utilize our sensors so that they can be integrated with different types of robots for feedback-based sensing and control of actuators. So today I'm going to focus on those examples. All right, what's the novelty of soft electronics compared to others? I believe that this picture captures something that I'm trying to tell. So you are seeing two different types of electronics, one on the wrist, the other on the fingers. Okay, on the wrist, you see the conventional rigid wearables that I'm wearing and some of you are wearing as well. It's smart watches, smart wearable devices. It's wearable, however, if you look at the details, they are made of rigid materials and rigid sensor, rigid components. Compared to that, you see there's different types of electronics mounted on the fingers. It's based on thin film, nanomaterial-based sensors, circuit interconnects, and miniaturized chip components, and everything, so that we can make a very small form factor device and platform. So overall, once you use nanomaterials and soft polymer, then we can have this exceptionally smaller form factor than conventional rigid electronics. At the same time, this device has wireless communication capabilities based on Bluetooth, RFID, NFC, and others. And more importantly, once you use these soft packaging miniaturization technologies, then you can put everything together as a single device platform. So like a Band-Aid, we can make this miniaturized wearable device that can be mounted on the skin, mounted on different types of surfaces, different structures, and so on. And also, once you control mechanics of it, then we can minimize those motion artifacts by having better contact to the target surfaces and target signal sources. And also, once we make it ultra thin, ultra light, and breathable, then we can have negligible thermal and mechanical burden. So the bottom line is that once you have all these factors, then we can have seamless integration of these sensors with different types of robots. Okay, you may wonder how we can design such soft electronics. So here in this picture, I'm holding a miniaturized rigid circuit, including sensors, wireless telemetry, and others. It's small, however, it's rigid. So the question is, how can we make it thin, soft, and flexible? There are many different strategies that you can use, and many different groups are doing different things, using organic materials, different types of manufacturing technologies, and so on. However, one simple example here is that we can simply change the materials. So we still utilize the off-the-shelf miniaturized chip components to maintain the functionality of the electronics. But here we changed the rigid plastic substrate to soft polymer, and also we changed the rigid metal to thin film nanomembrane metal so that we can lower the bending stiffness. So it becomes flexible even with bending, without mechanical fracture. At the same time, this thin film nanomembrane metal can be integrated with soft polymer. Then we can make a soft composite. Then from the mechanics, once you applied strain here, then we can get this outer plane buckling behavior of this core metal so that you can avoid mechanical fracture, right? So based on this simple strategy, we could design different types of nanomembrane electronics. We call it as hybrid electronics because we are using two different materials, like soft material and hard materials. So here in this computational modeling, you see that there are little boxes. Those are representing small chips or sensors. They are rigid, obviously, right? But now when you connect them with this nanomembrane soft composite, then when strain is applied, those nanomembrane interconnects can absorb the strain so that you can avoid mechanical fracture from the core components. So that you can maintain the functionality during multimodal bending and stretching. So based on that idea, we can build and manufacture different types of nanomembrane electronics shown over here. They can endure twisting, bending, stretching, compression, and so on. All right, today I'm going to briefly talk about 3 examples of these soft nanomembrane sensors and how we can integrate them with robotic systems. So one example is that how we can use sensors so that it can be integrated with soft earthworm robots. And second example is that how we can use soft sensors to be integrated with wearable sensory transfer devices. And the third example is to use sensors to make feedback-based human strength augmentation system. All right, this is the first example where we had collaboration with Dr. Hammond and Dr. Goldman here at Georgia Tech, and we published this work last year. In this work, we are trying to develop soft materials to make sensors and stretchable interconnects, and also miniaturized wire circuit to get the sensing data in real time continuously and wirelessly, so that we can control this soft earthworm robot fabricated by Dr. Hammond and Goldman's group. Okay, so in my group, we worked on sensors, obviously, right? So we designed this. I don't know whether you can see that there's little black lines. Those are organic material-based sensors. They can be easily integrated on the surface of this earthworm soft robot. And we have 2 different types of sensors, strain sensors and pressure sensors. And for example, here, a pair of strain sensors are using Whiston bridge, so they can get the data, and there's an embedded wireless circuit at this joint to transfer those data to a wireless receiver, so we can get those data to see what happens when this earthworm robot is moving and when this robot is hitting surfaces, things like that. So again, not a lot of details, but this is an example of a fabricated strain sensor made of soft polymers mixed with carbon nanoparticles, carbon nanotubes, and nanowires, and so on. And as you can see, that it's very soft and thin, stretchable, so that it can be easily integrated with any types of soft robots. Here, it's mounted on the surface of this soft robot without any mechanical burden. So this guy can have natural behavior of this robot motion. And these are video. I hope you can see it. OK, it's moving. So where we can actuate this robot component, right, having this longitudinal expansion, compression, and bending to the left and right. And at this joint, we have miniaturized wireless circuit that can deliver the data wirelessly to a receiver. Here, you can use any Bluetooth receiver to get the data so that you can have feedback loop control of your soft robot. The second example is to utilize the soft sensors so that we can make a wearable sensing suite. And we are going to integrate this with sensory transfer device actuators. So this is the collaboration with Dr. Hammond Group, and also we work with Dr. Cousin at Shriners Hospital in Philadelphia. So the overall idea is to improve the neuromotor control skills, and we are trying to deliver that sensory information to the user here, pediatric patients who lost their limb motor skills due to many different reasons. So as you can see from this illustration, there are two main components, one sensor suite, the other transfer suite. So in my group, we are trying to develop these different types of sensors like strain sensor, temperature sensor, pressure sensors, and so on. And once we measure those data when this kid is moving or touching something, those data will be transferred to the actuation transfer device so that it can have vibrotactile or mechanical tactile inputs to the user. So currently we are working on this wearable three-finger sensing globe where we can integrate strain sensors and pressure sensors. And now we are using this, as you can see from this video clip, we are using this nanomaterial printing method by using aerosol jet printing to print different types of nanomaterials. For example, here we are using soft polymers and also silver nanowires. They can be printed together to make a composite, and we can have ultra-thin strain sensor on top of this globe so that it can have strain change detection. Third example is to utilize our sensing capabilities now to develop wearable upper extremity robots. So again, I work with Dr. Hammond, great colleague. He already shown up 3 times. And also we work with Dr. Sinohara, a biomechanical person, who's helping us to analyze the muscle activity and motion behavior. So as shown in this illustration, this person will wear this upper extremity robotic system so that we can pick up the user's intention, whether he's trying to move something, lift his arm, or grab something. Once we detect that user's intention based on muscle activity or acceleration or gyroscope-based motion, then we are trying to deliver that inputs to the soft pneumatic actuators so that we can have strength augmentation. It can be used for age-related issues regarding like musculoskeletal health and other people who have issues. All right, this is an example of wearable muscle activity and also motion sensing device. So this single device platform, like a Band-Aid, it can be simply mounted on the skin to measure electromyograms and acceleration changes and orientation changes. It has multi-layers shown over here. But the good thing is that we can make different types of sensors that can be mounted on different locations. So here we are targeting to have 5 different muscle detection as shown over here. And in this video, as you can see that this guy is wearing these devices, and we are using Bluetooth and customized app to have real-time continuous detection of these activities so that it can deliver the information to actuate soft pneumatic systems later on. All right, with that, I'd like to summarize. As you saw that we are working on various types of sensors in electronics. And obviously, if you're interested in this domain, please let me know, email me, or if you want to get details, please visit our website. I'm very thankful for research sponsors, and also I thank you for your attention.